Hi everyone, my name is Claire Tomlin. I'm a professor of electrical engineering and computer sciences at Berkeley, and this is the 28th module in a series that we're recording to support the course EECS 221A, which is linear system theory at Berkeley. In this module, I'm going to construct through example a Jordan form, given information about the characteristic polynomial and the minimum polynomial of the matrix. And I think this is the most concrete way to understand Jordan form, is to do some examples. Okay, so Jordan form. And remember, in the past few modules, we've been motivating this. We motivated it originally by thinking about a similarity transform that took us to diagonal form. But that was only possible to do if the matrix had n linearly independent eigenvectors. And we don't have that anymore in general. Okay, so let's think of an example. Okay, so this is very specific. This is not general yet. But we're going to consider a matrix A that has a characteristic polynomial of s minus lambda. Okay, we're going to use D1. So actually, there's only one eigenvalue, and it's repeated. It's at lambda. And in this case, D1 would be equal to n for an n by n matrix A. Okay, so the minimum polynomial here is going to be s minus lambda to the m1. Okay, so let's suppose, for sake of this example, that we have a 6 by 6 matrix A. Okay, so this is just the example. We have n is equal to 6, so that means that D1 is equal to 6. It's equal to n. And let's suppose for this example that m1 is equal to 3. Okay, so we've got a minimum polynomial. We have, as introduced from the last module, the largest Jordan block is of size 3, associated to that eigenvalue at lambda. Okay, so what does this tell us? Well, it tells us a couple of things. So in this example, we're going to suppose that we have, again, it's just one eigenvalue which is repeated at lambda. And we know that the difference between the dimension of the matrix A and the largest Jordan block is 3. Okay, so that tells us that we could have 2 Jordan blocks of size 3, or we could have 1 Jordan block of size 3 and a Jordan block of size 2 and a Jordan block of size 1 to get up to the dimension n. Okay, so in this example, let's suppose that the null space of A minus lambda I, okay, so remember this is how we compute the eigenvectors of the matrix, is dimension 3. So it's the span of 3 eigenvectors, E1, E2, and E3. All right, so this is part of the example. Let's suppose that the null space of A minus lambda I squared is equal to, so it has to contain the null space of A minus lambda I, so it's already got those 3 eigenvectors in it. But suppose you can add 2 more linearly independent vectors into that null space, and that's V1 and V2, we'll call those. And then let's suppose that then the null space of A minus lambda I cubed, you finally get the 6 dimensions. So it's E1, E2, E3, V1, V2, and we'll call the third one W, or the 6th one W1. Okay, so basically what this is saying is, so what this one is saying is A minus lambda I E1 is equal to, or sorry, yeah, that's right. A minus lambda I E1 is equal to 0, A minus lambda I E2 is equal to 0, and A minus lambda I E3 is equal to 0. What this is saying is that V1 and V2 are linearly independent solutions of the following equations. A minus lambda I x is equal to E1, A minus lambda I x is equal to E2, and A minus lambda I x is equal to E3. So you take those 3 equations, and there are 2 linearly independent solutions, V1 and V2. Okay? So that tells us that V1 and V2 belong in the null space of A minus lambda I squared. Okay, and then finally, A minus lambda I cubed allows us to complete up the null space. So here we have that W1 is a solution to A minus lambda I x is equal to V1, or A minus lambda I x is equal to V2. Okay, so that's where W1 solves one of those. Okay, so we solve these equations to get the VI's, we solve these equations to get the EI's, and we solve these equations to get the W1. Okay, so let's now write out what we have. Okay, so we have that the span of the EI's, the VI's, and the W1 gives us R6 because we have a 6-dimensional system and there's 6 vectors in it. And so now we can write out these equations. Let's actually write these out in terms of our eigenvalue, eigenvector notation. So we have that, so let's just sort of summarize. We have that A E1 is equal to lambda E1. A E2 is equal to lambda E2. And A E3 is equal to lambda E3. And now these equations here give us so let's suppose without loss of generality that V1 and V2, they solve these first 2 equations when the right-hand sides are equal to E1 and E2. So it's without loss of generality because the structure would be similar if it solved these 2 equations or these 2 equations. But what we have, if the V1 and V2 solve these 2 equations respectively, then we have that A V1, so we're going to follow on from these equations here. A V1 is equal to lambda V1 plus E1. Okay, that comes out of this equation here. And similarly, A V2 is equal to lambda V2 plus E2. And then let's suppose without loss of generality that W1 solves this first equation here. It could solve the second, and it would be similar, but let's just suppose it solves the first. So we end up with A W1 is equal to lambda W1 plus V1. Okay, so that comes out of this equation here. So we have these 6 independent vectors, E1 up to E3, V1, V2, and W1, which solve these equations here. The EI's are eigenvectors of the matrix A. The VI's are called generalized eigenvectors of the matrix A of degree 1. Because the equation they solve of degree 1, because E1 and E2 themselves are eigenvectors. W1 is called a generalized eigenvector of the matrix A of degree 2 because V1 is already once removed from the eigenvector E1. Okay, so we have 3 eigenvectors and 3 generalized eigenvectors. They're all linearly independent from each other. Okay, so now let's consider constructing a similarity transform in a similar way as we did for the diagonal form. We don't have 6 independent eigenvectors, but we have 6 independent eigenvectors and generalized eigenvectors. So we'll use those in the column of the matrix T inverse, which we use in our similarity transform. Okay, so again, this is just an example, but it's an example which illustrates how we construct a Jordan form. Okay, so I've got my 6 equations there. Okay, so now I'm going to construct a matrix T inverse, and I'm going to order the vectors in the following way. So I can think about this row here as a chain of eigenvector, generalized eigenvector of degree 1, generalized eigenvector of degree 2, but they're all coming from the eigenvector E1. Because V1 is related to E1 and W1 is related to V1, which is related to E1. So I'm going to start with my first chain of eigenvectors, generalized eigenvectors. So E1, V1, W1 are the first 3 columns of the matrix T inverse. So these are column vectors. Now I'm going to start with my second chain. V2 is related to E2. So E2, V2, and then finally I have a last eigenvector over here, which is E3. All right, so if we construct this matrix, these are linearly independent vectors, so I can compute its inverse. In particular, I can compute T. And I go through the same thing that I did before for the diagonal case. So if I look at AT1, and we can write this out. So let's actually write it here. We'll use what we've already done. So AT inverse is equal to this matrix here. So it's going to be T inverse times the following matrix. Okay, so this is no longer a diagonal matrix, but from these equations we can construct what these elements are. So AT inverse, so A E1 is equal to lambda E1. Okay, so there's a lambda here. Now A V1 is equal to lambda V1 plus E1. So I have a lambda V1 plus E1. So that gives me a 1 up here on the superdiagonal. And then what do we have? A W1 equals lambda W1 plus V1. So a lambda on the diagonal and then a 1 above it. And then this up here is a 0. And then everything else here is zeros. 4, 5, 6. All right, so that's the first 3 columns, and now we go to the second row. AE2 is equal to lambda E2. AV2 is equal to lambda V2 plus E2. So it's a lambda 1, like that. And then finally, AW1 is lambda W1, sorry, AE3 is equal to lambda E3. So that's just a lambda here. Okay, so AT inverse is equal to T inverse J, where J is called the Jordan form of the matrix A. And in general now we can write post-multiply by T here. So A is equal to T inverse JT, where J has this following form. So let's take a look at it. We have, it's a upper triangular matrix where we have the eigenvalue lambda on the diagonals, and on the superdiagonals we have either 1s or 0s, and then everything else is 0. Okay, and associated to the lambdas, so depending on whether or not we have an eigenvector, so you can see that all the columns that are associated to eigenvectors are all 0s, but columns associated to generalized eigenvectors have a 1 on the superdiagonal. And from this we can derive what we mean by Jordan blocks. So I can represent this matrix as a diagonal, as a matrix whose diagonals are blocks. Or sorry, as a matrix who has diagonal block matrix entries, or who has block matrix entries on the diagonal. And in this case, I have a block, and then everything else is 0. So I have a block, which is a 3 by 3 block associated to the eigenvalue lambda, a 2 by 2 block, and a 1 by 1 block. So this is called a Jordan block of size 2, or sorry, a Jordan block of size 3, a Jordan block of size 2, and a Jordan block of size 1. And that Jordan block of size 3 came from the fact that there was 1 eigenvector and 2 generalized eigenvectors associated to lambda when the eigenvector is E1. There is 1 eigenvector and 1 generalized eigenvector associated to E2, and 1 eigenvector associated to E3. There's no generalized eigenvectors. Okay, so that's an example where we constructed the similarity transform. So this matrix T inverse, it's invertible, and this says that for any n by n matrix A, you can construct a Jordan form by constructing eigenvectors, and then really these are just mathematical entities that we define as generalized eigenvectors. The point is that you can always define n, or in this case 6, linearly independent vectors, which gives you a similarity transform of A to the following form, which for the non-diagonalizable matrices is as simple as you can get. Okay, so we have that Jordan form for our case where we had a 6 by 6 matrix with basically 6 repeated eigenvalues at lambda. What would happen if you had a general Jordan form? You might have, so in general, you could have a Jordan form that looks like, suppose you had a characteristic polynomial, which was of S, which is S minus lambda 1. Let's just suppose we have 2 eigenvalues, and we can generalize this to n. And that was 3 and S minus lambda 2, which was of dimension 2. So this is a 5 by 5 matrix A. Let's suppose that the minimum polynomial, so I shouldn't really say in general, but more generally, let's say, because we're still looking at a specific example, more generally. But now I've expanded to 2 eigenvalues. And so let's give this one, let's suppose it's just S minus lambda 1, and let's make this one S minus lambda 2 squared. Okay, so the minimum polynomial is of degree 3 in this characteristic polynomial of degree 5. So just from that information now, you can construct possibilities of what the Jordan form looks like. So what this says is that the largest Jordan block associated to eigenvalue at lambda 1 is of size 1. So that tells you that the Jordan form for each of those, the largest Jordan block is of size 1. So I'm going to get 3 little blocks of size 1 associated to the eigenvalue at lambda 1. And then the largest Jordan block associated to the eigenvalue at lambda 2 is 2. So that should be lambda 2. So that tells you that the Jordan form is going to look like this. Now, we say the Jordan form will look like that. That's up to permutation. So I could have reordered the eigenvectors and generalized eigenvectors in this case. So I might, have this block appearing here and these smaller blocks appearing here. We consider that the same Jordan form, up to permutations of the Jordan block. Okay, so in this case, this gives us only one possibility for the Jordan block. Let's see, could I have had other possibilities? 3, no, because if I had 2 here, 2, that would have specified that I would have had a Jordan block of size 2 and a Jordan block of size 1. That's the only way to get that here. But in different cases, if you're given the characteristic polynomial and the minimum polynomial, you can come up with constraints on what the Jordan form looks like. All right, finally, let's conclude with why this is useful. In the diagonal case, the whole point was it's useful because you can come up with a formulation of e to the at more easily. So we remember that e to the at is equal to e to the, in this case now it's going to be, so a is t inverse jt, which we showed before is t inverse e to the j t t. So it's really this that we're interested in computing because we can always get back and forth to e to the at by pre and post multiplying by these n by n invertible matrices. Okay, so we have then a general result which tells us, so just like we had for the diagonal form, for the Jordan form, if the general Jordan form, well, let's just use the example that we have above, looks as follows, then e to the jt, well, we can do a more general example as well, but e to the jt will have quite a specific form, and it can be computed just by inspection. So just like in the case where we had the diagonal form, and we could do it by inspection, if this is, let's actually do a couple of cases. So if we'll separate ourselves from this example here. Suppose we had a Jordan block that just looked like one, or a Jordan matrix that just looked like one Jordan block. So lambda's on the diagonal and 1's on the super diagonal. So that's a Jordan block of size n. Then f of j, or e to the jt, is going to look like e to the lambda t on the diagonals, just like in the diagonal case. So the eigenvalues of e to the jt are e to the lambda t, where lambda is the eigenvalue of j. And then on the superdiagonal, we'll have the derivative of e to the jt. So that's lambda, or let's just call it e to the lambda t derivative with respect to t. So d by dt of e to the lambda. E to the, this is with respect to lambda. Actually, let's be a little more general. Let's suppose we had this matrix J, and we were computing a function of the matrix J. So we can generalize, or we can make this specific to e to the lambda t in a second. Then what does f of j, a function of j, look like? This is f of lambda on the diagonals. Okay, so this is a function. In our case, it's e to the at, but in general, this result holds for any function f which is analytic on the domain, on the spectrum of A. And what we have on the superdiagonal is the derivative of f with respect to its independent variable, so s or whatever, and then evaluated at lambda. And then on the super-superdiagonal, f double prime of lambda over 2 factorial, f double prime of lambda over 2 factorial, all the way up to the top right corner element, which is the n minus first derivative of this function f, evaluated at lambda over n minus 1 factorial. So that's the general form of a function of a matrix, if the matrix is in Jordan form. And if we had a more general form, so suppose now our J looks like it has several Jordan blocks. Okay, so let's just do an example similar to the one we had before. So let's suppose I have 3 eigenvalues at lambda 1. Actually, we've got a Jordan block of size 3 here. Let's put a Jordan form. Let's put 2 eigenvalues at lambda 2, and let's put a 2 by 2 Jordan form there. Then you can just take this result for f of j and extrapolate it. So here f of j is so we have f of lambda 1, f of lambda 1, f of lambda 1, f of lambda 2, f of lambda 2 on the diagonal. And then on the superdiagonal, we're going to have f prime of lambda 1, f prime of lambda 1, and then f double prime of lambda 1 over 2 factorial up in the corner there. Okay, so there's a 3 by 3 block, and the rest are zeros. That comes from this Jordan block. And then the only other non-zero elements are the Jordan block down here, and this is just going to be f prime at lambda 2 and a 0. So this always holds. If we have a Jordan form and we have some function f that's analytic, basically that means that it can be expressed locally as a polynomial around the eigenvalues of the matrix J, then we can construct, given J, we can construct by inspection a function of that matrix J. So now you can take that and you can extrapolate to suppose f of s is equal to e to the st. And so we take the derivative with respect to s of e to the st, and we can compute this matrix e to the jt, which is what's needed eventually to compute e to the at. Okay, so we've talked about really 2 things in simplifying this computation of e to the at. We've talked about a diagonalization, which is a similarity transform in the case where we have n linearly independent eigenvectors that allows us a very simple form of e to the at. And then similarly, in general, we've shown that the generalization of the diagonal form is the Jordan form. And in that case also, we can write down e to the at by inspection, just by knowing the Jordan form. And we know how to compute the similarity transform that takes us to the Jordan form. All right, so now we'd like to move forward and think about how we're going to use this in systems analysis. And that's the topic of the next several modules. Thanks very much.